Thank you for coming. We will try to provide constructive feedback to group mates. And there is a hope that there will be 2 people more. Okay. All set? No more copies? Huh? Okay. Need to run and bring more so that it's sufficient. So there will be people more back in mind. Children will come forward and also show the first tutorial status really. And last time I was mentioning that there will be an opportunity to try, no guarantee, but try to go to the Pacific conference array, which is yet to be used. I was wrong about deadline. It's not February 1st, it's like April 15th, which is enough time to fill out the text, fill out rush. And I was just going through the web page to maybe once in the future I'll show steps, but basically everyone can go just create an account on the website of the content as a beginner and start preparing a play. If there is an open question in which section to apply, you get better order. And there are several sections. Like computational, physical, and knowledge, and each of them there are a couple of dozen options. So I'll send this file. It's more rush, but we review and decide whether to spend an invitation for this accidental charge dynamics, but we need to serve the all constructs of the code. There is very low chance for computing anything included with the same first position. So highlights of the opportunities, dynamics, technologies, and one of the sections that equals dimension materials, Right now we are not doing active fronting on, but there is a section that can be if you are doing the past programs. Methods, molecules, culture fast there are too many options to take a decision immediately. So maybe it's submit. And there is a perovskite in the image section. Yeah, it's called the website. So the deadline is 15th? No, April 1st. Still. So we start this I miscounted the prints. I don't know if it's productive if I run and bring more or better. We go with whatever we have and just provide verbal feedback and review on the recording. So little about half an hour for each. So June don't hesitate to stop the speaker and ask those questions. You don't know from what to start from.
That's pretty much what I have here.
Challenges, like who needs this usage, why you select this one. The audience will be, this draft is not only for coming meeting, it will be used for recycling for several meetings. And there is a chance that audience will be ignorant either in theory or in materials that you may just attract attention first and then go to this.
So I'm looking at the the photovoltaic properties of perovskites, and I'm looking at two different types of systems. First, I'm looking at the organic inorganic system, and I'm also looking at a completely inorganic system. And the reason that we're looking at these is the perovskites have a good photovoltaic properties, such as the charge transfer, but they have relatively low stability, and the organic inorganic systems can't have the ability to offset the stability issue compared to the 3D bulk systems.
Mm-hmm. No one needs a logical connection to what you are actually doing.
Yeah.
You're not measuring stability.
I am not measuring stability. That's the reason I'm interested in these materials.
Uh-huh.
What I am looking at is examining is based on the stability of these materials, trying to find what material performs better. Has a better performance based on the size of the perovskite layer.
So you're doing structure to property relation.
What?
Structure to property relation.
Yes.
What is the key metric or observable that characterizes how if it performs worse or better?
relaxation breaks.
Should it be quick or slow?
For the material we're looking at, we want slower relaxation.
Okay. No matter whether it is truth or not, now it's your selling point. You should try to sell it. Relaxation like this. Okay.
That the slow relaxation rate allows for a greater time for the charges to separate,
Okay.
which is how current is generated in photovoltaic cells.
So we have defined the engineering challenge for general applications. And is there available free code to compute this relaxation rate, where you need to make an effort yourself to program something or connect several codes together? Like, is there a challenge for methods? Is there what's the nature of relaxation, where it comes from?
It's
You don't hesitate. It's
difficult.
well, but you already have some results.
Yeah.
And you just need to put words around them. Ideally, you may want to add a little bit more results, but already if you want to present this one can put a 40 pages composition explaining them. Like, can you point in your bluish-greenish diagram and tell what is going on? What is relaxing there?
So here, this top dashed line is representing the electron, and it's excited to. This one's excited to hold +9.
Those are technical details, but what is the time on this?
The time is.
And x-axis is time, right?
Yes, x-axis is time.
So what happens with time?
With time, the electron and hole return to the band edge.
How does energy of electron changes with time? What is your y-axis?
The y-axis is the energy.
And what happens with yellow stripe?
It goes down.
Okay, so what happens with energy of electron?
It increases.
Can you define relaxation based on this?
It's going from a higher energy state to a lower energy state.
Yes. So it's your definition of relaxation. Is there public code that you can purchase or download from online to do this? Good. What's the nature? Why energy goes from higher level to lower level? And does it contradict with energy conservation?
It goes from a higher level to a lower level, releasing the energy.
Where?
As either heat or
What is heat?
Or
What is heat?
phonons or photons.
Phonons are sufficient. So interaction between electronic states and phonons. Which of your equations describe it? Let's play what if you're going from top to the bottom.
Density states, absorption spectra, or absorption.
So, first equation that relates to interaction between electrons and phonons. Is equation number 1 up? Yes. Okay. So this equation is not typical in standard Bohr-Einstein approximation, and you're trying to go beyond this. Can you go into explanation of what this equation describes? And maybe some comments where it originates from.
So this equation is describing the interaction of different orbitals with each other based on their different electron states. And it comes from red field theory.
Yes and no. There is matrix element of electron interaction, which comes from this your V sub ij univariate coupling, and this information can be funneled in can serve as an input to several competing theories that target the same quantity. Red field is one of them, but when you compute non-derivative coupling, it doesn't necessarily mean that your next step will be red field theory. You can go to surface coupling. So let's leave everything after this equation number 3 for later and just skip what does it represent and where it originates from. So it's more fundamental than red field theory.
What's big R and what's little r?
Positions. Nucleus. Electrons.
Are they so? In the equation, the symbol phi for Von-Schramm orbitals enters twice, right?
Yes.
As far as I can see from this distance. And
it still looks like it.
okay, and is the uppercase R is uppercase R the same in first and second instance?
No.
Can you evaluate why and what does it mean?
So we're looking at it in 2 positions of time. We have our first position, and then a short time later in a format of electron.
Okay. So what would be if delta t in the second part of this equation equals 0? What will be the ij?
correlation?
No. Autocorrelation is like equation 4 and further. But we are focusing only on non-adiabatic thing. The question is not
Oh,
about
it'd be 0
0 if I and j
if
are...
they're orthogonal.
Yes. Good. So, and if delta t is bigger than 0, then orthogonality is broken.
Yes.
So why orthogonality is broken? What's the reason?
Because we've changed the location of our position of our.
Positions of nuclei. And it induces change in the shape of electronic orbitals. So your V sub ij is characterized response of electronic states only to change of nuclei, which means electron to nuclei interaction. Now you have an idea what to write and explain this equation. Okay, leaving Redfield theory for the next time. Which observables you plan to show in your results section?
So the relaxation rate and electron position by time. That makes sense.
So, relaxation rate will keep us busy enough. So, what is relaxation rate and how we define it? And do you have in mind any equation that is not included here, but you always wanted to include it?
So relaxation rate is the rate at which the electron hole relaxes to the lower energy.
Okay. Can you show it in your diagram?
Here. See that yellow goes down.
Okay. But if I am a robot without eyes that just have this figure in numerical format, what is the algorithm? How do I find this time that you are indexing by your finger? Is there an equation that illustrates this blue diagram in your equation?
I want to say it's this one.
Let's try another guess.
Oh.
Let's move your finger to the right a little bit more. Yes. So can you explain this equation and tell what it is? And by the way, there is a hint. If you do not know what to say and you need to populate white space, after each equation you explain what each symbol means, and then the whole poster is already populated. So
we're
please go forward.
looking at the energy time.
So this equation has the letter delta n. Delta n is not energy. How does it connect with energy?
energy of orbitals in it.
Probability that orbit at a given energy is occupied at a given time, something like that. But your delta n depends on energy and time, and it is equal to subtraction of two terms.
Yes.
What are those terms, and why they are subtracted?
So the
Like, why one of them has time as an argument and another does not?
because we're looking at the time compared to a relative energy.
Relative, or
Or
you wanted to say the word equilibrium distribution, right?
pretty much.
Okay.
It's not really thinking it through though.
Equilibrium distribution. So in your blue figure, there is a yellow stripe
Yes.
and there is a dashed line across it.
Yes.
So what is this dashed line?
The dashed line is the visualization of the relaxation juice.
This is correct, but it is very like lay language, if adding a little bit more certainty. So at each instant of time, this dashed line takes on the one value. And y-axis is what?
Y-axis is energy.
So dashed line shows value of
Energy at a specific time.
yes. So how to find energy at a specific time if you already know the distribution? You can ask help with the clock. Please ask help with the clock and just. Just check if anyone wants to help.
So
What was the question?
how
So each orbital has an energy. And then the orbital occupations change in time. So then the average energy will change in time as well.
So you will want to proceed with this.
Oh yeah.
And I can make mistakes, but you can ask your friends and colleagues to correct. So, what are the conclusions? Because we need to give time to other group members.
In conclusion, we see that the increasing the size of the perovskite layer increases the band gap, which is the expected result, and that the inorganic system, the totally inorganic system, that's relatively quick message. I did write down the next version that didn't send to me yet.
Okay. Are there chances that such bluish-greenish figures will be ready for all systems in like a week or two?
Yes.
Good enough.
I was having some issues with the was one that I was hoping to talk to someone about, but I had these issues about an hour ago.
Okay, let's talk in person maybe at your place.
Yeah.
Let me invite everyone to thank David for presentation. And do not disappear. Maybe there will be questions or comments right away.
What's the connection between these three models?
So if we look at the first two models, the difference between those is the size of the perovskite layer. So here we have 4 spaced out a little bit wrong with my fingers, but where here we have 1 layer. And the connection with the second system is or with the inorganic system is comparison with a model that does not have the hybrid layer to see how that affects the dynamics of the models.
From title, it says your main focus is just the surface elements, right? Did you change your surface elements?
Oh, I didn't change the title from the template I used in this version, apparently. So the role of the surface elements shouldn't be on there at all, because I have no surface elements in my model.
Satisfactory? More questions? No? Okay, then let's thank David once again. And please collect the feedback. So, would you like to show?
So I guess I just make these figures. I do not have time to analyze it, so maybe we can do it together. So I guess in this work, I'm focusing on a perovskite solar cell. So here is my model. So basically, we have 3 components. Now the perovskite, and this is the electron transport material, and this is heat transport P. So this, the top one is the dynamic casting, and this is the composition. Bottom, we have an organic dye. So it's up there. I guess experimentally and computationally, the charge carrier dynamics in this kind of system is very rich, I guess. But the main novelty of this work is we introduce external electrical field, and then we investigate how this external electrical field influence the charge carrier dynamics. So, here I just show the density states for this system under different electrical field. So here is the energy gap. Interestingly, there is a linear relationship between electrical field and the band gap.
And there is no zero, no negative gap.
Yes, maybe.
Or maybe the orbitals that were constructing gap swap the order, but then if you formally just homolum, it comes to zero and then starts growing, or just staying zero if the bands are mixing.
I guess I need to double check.
And is it okay to interrupt in the middle?
Yes.
So the labels A, B, C, D and points on the right panel. Is it correct to say that like A is minus 0.3?
Yes, it's all consistent. It's from 5 down to minus 0.3.
And I'm talking about the upper density of states,
Right, it's all consistent.
like upper and right. The gap as function of electric field. What did it be called?
It's actual.
Like, is it correct to say like this is A, this is B, this is C?
Or it's different for the second order.
Can you maybe mark here or just explain? Oh, no, I don't know. Right, but even just so the word.
So I guess this form corresponds to NOE.
Okay.
This one corresponds to quantity.
So it's-
3 to 3 intensity.
Oh, okay, so it's reverse order.
Right.
Okay.
I guess what I want to point out, so I guess the particle charge density states is kind of interesting. So basically we have 3 components, right? So if you apply external electric field, basically you just shift each component of the density states. There is no any other changes.
The cover for dye and perovskite hard to distinguish. But is it correct that the conduction band moves to the negative as we move from E to A?
Right. Okay.
Yes. And the valence band probably goes in the opposite direction.
Right.
Okay. Is there a way to, so it's quite simple, if it is linear, then it's just dipole moment times electric field. So one can probably fit this trend into a simple equation.
Yes, but I guess we still need to double check the panel to see the structure of the overall shape of orbit is not small overall.
Mm-hmm. I'll try to add something. like matrix. So static dipole of Luna orbital, static dipole of Homo orbital times latitude. And if we measure these values at 20 and 24 lower latitude, there is a chance that it will reproduce this kind. Sorry for interrupting, please keep going.
Yep. So, because here I just show the observer spectrum. And, so yes, here is the expanding region of the from 0 to 2.5 megavolts. So clearly, you can see when we apply positive reaction field, also band gap is shrinking. So we have this kind of peak here. And if we just decrease the reaction field, we can see the shift of this peak.
I do have a question. Curiosity. Two-fold question. Is it possible to draw this absorption in log scale in Y? Is it possible to tabulate the value of absorption at transition energy equals 0 for each value of the electric field? So if we do it without logarithm scale, it will be like 0.01 for this value, and all the rest will be 0. But if one will do it in log scale, it will be 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. Which there is a relation in the equation that is corresponding to the absorption of 0 position energy. So it can be immediately converted into current voltage. And so that will be the rest of the So let me just keep going.
Now I think I'm not totally understand why this peak is much higher than the rest of them. Significantly higher than
Blue line is the reference without electric. Dark blue, not cyan, but
yeah.
And do you have interpretation of the peaks, like charge transfer shouldn't contribute to the optical absorption, so there could be like 3 types of peaks qualitatively: unoccupied on perovskite, occupied on perovskite, unoccupied on dye, occupied on dye, and unoccupied on titanium dioxide, occupied on titanium dioxide. So 3 types of transitions.
Yes.
Is it possible to label them in the, at least for the blue line?
Yes. Okay. And I guess if we see some major peak, that means it's transition within the Pascal, right? guess maybe this big. Also, this small features is from electron transformation.
Mm-hmm.
It might be too if we just extended the plot to like 4 EV, like those other curves might show it. Increasing onset.
Yeah, that's true. And here I just show the chapter dynamics. Because since the trend is a little bit weird, so at 0.05, the rate for electrons will be very high. But if we decrease the electron field, the rate decreases a little bit, but finally it just equals. So I guess maybe there are several factors. So you have the subgap, and also it's also related to the distance, like how many angstroms the carrier needs to travel. And spatially.
So the trend in the charge distribution in space, so that at positive voltage, the charge transfer happens earlier, and as you go to the lower voltage later. Is it right or not quite?
If you go to negative 0.03, speed just increase.
Mm-hmm.
Because for both electrons holes, if we do not have this set of data, seems we have a very good trend.
Mm-hmm.
What happens for this kind of data?
So this minus 0.3 is an outlier from the trend.
It seems like your charge kind of starts on the molecule, on the TiO2 to begin with. Just from your space charge distribution plot. So it looks like the initial condition is a perhaps type 2 titanium absorption. So that
Yes.
might.
This cannot be true because also data strength is very high. That means it has to be phosphate or titanium to titanium.
You would think, but I don't know, just based on the two dark red curves, I assume both of those are on the titanium. So it's either it starts there or it moves there a lot quicker. For some reason. on your cluster, are the oxygens coordinated at the surface?
I also check the frequency the octaves along the phone. And if there's chemical on receiver. And also the bubble aspects of this is 2.6.
There is a possible way to add clarity, but I'm not sure that one needs to do it. It would be too expensive. Remember the two-dimensional images. Jackson also one was doing by doing this dynamics in space, not one dimension but two dimension. So if one would do it, it would be a little bit more clear. It may not work for a poster because it's like moving and it's too many snapshots. We have this cool symbol. So if it is needed, we may try to use it, but it could be not justified amount of effort.
I would just compare or look at the LUMO plus 12, plus 13, and plus 14 orbitals. And see if they all roughly look the same.
So in the table there are rates of energy relaxation, which are based on the how expectation level of energy changes with time. Is it reasonable and is it possible to compute rate of charge transfer by fitting the expectation value of position out into some function? It may or may not coincide with relaxation level.
Yeah, of course. If I look at this one, it seems to go up with the down.
The orange goes up. Oh, for blue, yes, it will be some strange effects, but it could be. One may find some interesting physics from it. It could be possible just to make it instead of energy find expectation value of position. But thank you. Other questions, or objections, or comments? Questions one, questions two, questions three. Thank you once again, and please submit the paper.
So this poster is about the magnetic field and from dynamics in graphene. So graphene shows unusable band structure. So it has the conduction band and the valence band touch each other at 6 corners of its Brillouin zone. And their energy dispersion is linear. around this electron. That's why electrodynamics appears. This is really important for optoelectronic properties. So here you can see the grand structure of graphene. I just zoomed in one grid point here. Although in here it shows the valence band and conduction band. There is a gap between them, but in zoomed in image there is no gap. So we are overlapping a little bit, not much. That's why graphene is semi-metal. In method, there are more equations. I will put them later on here. Since graphene has a honeycomb triangular lattice structure, it can be described with the type Hamiltonian equation. Here it shows the graphene lattice structure. So here are two atoms here, A and B. So if we consider A, there are 3 atoms. They are nearest neighbor, and there are other these blue atoms are next nearest neighbors. So this term in Hamiltonian Hamiltonian for nearest neighbor atoms, and this second term is for next nearest neighbor atoms. And this is the unique cell inverse properties, which is calculated well. So at each corner, if we consider this one is K and this one is K prime, and in between, in the middle, there is a point of X. And at the center of this realism gamma. So if there is no magnetic or external magnetic or electric field, the energy band structure, one can get energy band structure from the type bending equation, this one, here plus for conduction band and minus for valence band. And Fk is defined by this equation. There are more equations I'll put here, those are for corresponding to these figures. So what happens in this figure is, this is for free electron. If we apply magnetic field to free electron, you can see.
Free electron. Okay.
Here it shows these values are magnetic field values, and these are the time steps. As we can see, for free, it looks like there is no electron dynamics yet. Here, maybe there is some. Since if we look at the top of this figure, then as here we can see for magnetic field 0 point. By the way, this one is for graphene. So if we apply magnetic field in graphene, we can see electron dynamics. This yellow space is high electron density. So for magnetic field 0.005, we can see how electron wave packet changes, and for magnetic field 0.012, we can see the wave packet is spreading here. But I don't see any. Apparently, it looks like there is no dynamics here for this values in free space. So what I think I need to work more on these values, probably I can increase the value of magnetic field here and put corresponding figures here. But there is a problem is that for this current computational settings, we cannot apply a higher magnetic field. If we apply high magnetic field, then there will be quantum Hall effect and Landau levels will create that different story. So electron should satisfy direct equation instead of non-relativistic Schrodinger equation. That's why I'm afraid to put high magnetic field values here.
Just a quick ask questions as you go.
Yeah.
You allowed to ask questions?
Sure.
So if there is a standard wave packet code for one dimensions.
So you're doing this in this code for sure, and David was using it a little bit in rotation. And Aaron had a copy of the code already, but not part of the class. So in case the motion of the wave packet, and there could be connection between two-dimensional and one-dimensional case. I'm talking about one-dimensional because it's simple. In case the motion is not detectable for human eye, it doesn't mean that there is no motion. And for such cases, there are procedures of converting the distribution of function or wave packet into expectation values. Like expectation value of momentum.
Yeah, I do that. There should be
an expectation value of the variance, like how standard deviation. And even if the center is not yet moving far, definitely in your graphene diagrams, one can see that the
center is moving.
Center is moving, and the variance, the broadness, the uncertainty of the wave packet growth. And this is just one line as function of time, which can be possible to show in the remaining time.
Okay, so that I can keep these values then. Just get the expectation values.
Yes. Keep going, or it was all?
Yeah, that's all.
Okay, but thank you so much.
There should be one more row here corresponding with this magnitude. And there will be one more figure. I am not sure if in this poster, probably, of the expectation values.
Good. You can try to see behind your computer when the code is running. Set up the data, and you might try to approach if you will be willing to code, just shorten the part of the code and get some ideas what to change.
That's the expectation value?
Yes, yes.
I don't have the code. You asked me to
the
generate
version of the code that is running, that you have on your laptop, just approach anyone in the group and check how to add expectation value to the, if you will, like 1 or 2 lines.
Oh,
Okay. More questions?
So do all your blue figures come from programming the type binding?
this
Yeah, are all of them?
one? Oh, yeah.
Sorry, the figures that you got data on.
This one is from type binding. This is one from MATLAB board. I made it manually. This one I made, and these are from MATLAB boards.
Let me translate confusion
Oh,
from Aaron.
so is there?
There is a confusion. You didn't mention it in explanation, or maybe I missed it. Maybe I missed it as well. You're showing equations, and then you're showing results. And the nature of the idea is that these results are obtained with these equations. Is it right? No. You're showing. You do not show any equation for this wave packets.
No.
And for their motion.
No, I'll put them myself.
You will, but they are not
Right
yet.
now, they are not here. Yes.
So there are some other secret equations that will show dynamic of this snapshot wave packets.
Right.
That was the question.
Yeah, I assume if you had everything on your poster, you would have went through it. But like if this was somebody's first time, it's like it's not clear that those figures are wave packet dynamics.
Okay, there should be more equations here.
About probably some DFT. That's how you made your dispersion.
There is no
curve.
DFT here. It's all about the matrix.
See, it's not clear.
You said your bottom one's for graphene, right?
Yeah, level graphene.
We have a good discussion.
So
How can you do graphene without DFT? Teach us.
then did you get to the dispersions from your type binding?
this discussion here.
So,
This one, you mean?
so for your right figure, so you have a free particle, so
Yeah.
there's no potential to interact.
No, there is no
But then when you're
there.
graphene, it's like, what's the potential of the electron?
Magnetic field is applied here. It's like perturbation.
So, then the nature of question, even if I come in here for the first time and listen to the discussion, what is the equation of how magnetic field enters into Hamiltonian?
Exponential.
Can you,
So Hamiltonian,
how magnetic field enters into Hamiltonian?
or it's a magnetic field, dot product of magnetic field and angular momentum.
Yes. You right? Or you want to dig deeper? Which is okay.
So there, okay. So in graphene, there in carbon atom, each carbon atom there are 4 electrons. So here, if you look at it. So 3 electrons make bond with neighboring carbon atoms. There is in each graphene atom there is 1 free electron. So if you apply magnetic field here, they will move. That's why
Right.
we see the wave packet. And it should start from each corner, but currently we just consider 1 point here, 1 grid point.
That all makes sense. I guess the thing I'm confused about is
And if you are like when there is a free charge, and if you apply magnetic field, so according to Lorentz force, it will move in circular motion, cyclotron motion. That's why we see it will be moving this way. So it is spreading, and if the magnetic field is higher, we can see it moving in circular.
so if you have no magnet,
Yeah, here we have magnetic field, but without just free electron. We don't know. There is graphene here. Here we have graphene.
right? So I guess my point is, how do you account for the electron moving in the graphene sheet? You just say there's no.
So there, if we put Hamiltonian and these equations in the MATLAB code. Is that okay? I think so.
No, do not ask me, ask Aaron.
So they're analytical curves. So you just use the curves from type finding, as opposed to computing what the dispersion is in DFT and importing those.
So here, since it is not possible to apply magnetic field in DFT, that's why right now the magnetic field is applied by that equation in MATLAB code. Later on, there will be DFT for that non-adiabatic dynamic string sampling. That's what the plan, as far as I know. But I'm not exactly sure how this, how the graphene model is coming here. That was my question as well.
No, you have everything on your, about this question you have everything on your poster. There are, let me contribute. So I'm trying to show equation that Fatima wants to show to Aaron to satisfy this curiosity. There are two situations: free space and graphene. For free space, it's just quadratic dependence of unperturbed energy on momentum. And for graphene, it is analytical curve from type binding that is seen in the post.
Okay.
Okay?
So it's like you put an electron like in that cone,
Yes,
essentially.
or 6 cones. The concept of potential is not wide applicable because it is not, it's like kinetic energy term or total energy term, depending on momentum rather than position. So it's like a shape, potential like shape, but it depends not on position but on momentum, distortion.
Right.
And then either in free space or in graphene, this unperturbed Hamiltonian is enriched by magnetic field, where the angular momentum in momentum space is negative in similar way as in the Cartesian position space. And as soon as the unperturbed Hamiltonian is set up, Fatima is numerically solving time-dependent Schrödinger equation for a wave function that is depending on momentum in x, momentum in y, and time. And snapshots of this absolute values where x, p, y, time, y squared are plotted in this colorful diagrams as function of the value of time for different magnetic field. Is it what you wanted to say, Fatima? More questions? Fatima? And Florida, thank you for the question that you did for the really healthy discussion.
So then what is changing T? So that's like your hopping parameter. Below it, that, like how would you do in that experiment?
It's a time propagation.
No.
Oh, that's it.
No. There is an ambiguity that is not ideal. Wait, what we say, and then we reformulate the question. It's still persists. There is ambiguity in notation. The letter T is used twice. One for time, and another for hopping parameter for the probability of instantaneous jump from one special site to another special site.
Right.
The results section includes T that stands for time on the right hand. The T that is used on the left side in this this is hopping parameter. It's not time.
Right.
No way. It's like,
I could increase it by tau.
huh? Yeah, it's off diagonal element of the Hamiltonian.
Mm-hmm.
Good.
Yeah, I guess that makes more sense now.
And this work didn't set up a task to solve time binding equations. They have been solved like half a century ago, and they used only as a tool. And all these equations are not new; they are shown only for introduction and clear definitions. So the equations that are being shown right now, they are not original. They just borrowed from literature, right? So we're just at the beginning of getting original equations.
Original equations are not here.
Okay, because they're highly secret. More questions to Fatima? Okay, then thank you once again. And please collect the feedback and try to implement it. Now for yours. You need another table to put your laptop.
I think I can do this. Alright. Hi everyone, I'm studying excited state dynamics in one-dimensional thermoelectric materials, specifically lead, telluride. So it's common knowledge that we all want to maximize the thermoelectric effect in certain materials, and in order to study, and in my case, in order to study the thermoelectric effect in materials, we computationally compute their electronic relaxation rate. Generally, where electronic relaxation rate is correlated with the high thermoelectric effect in materials. So what I did was I looked at approximately 300 atomistic model of a lead telluride nanowire.
300 what? Is it okay to interrupt you in the middle?
Sure, sure.
So 300 what?
So the lead telluride nanowire I'm looking at, it has approximately, I calculated 300 atoms.
Okay, good. Is it stoichiometric?
Stoichio,
Means like if the chemical composition is PBX TEX, or TEY is X and Y the same numbers, are they balanced?
yes.
Okay, then you can tell stoichiometric.
All right. Okay, so they're stoichiometric. So I'm computing electronic relaxation rates for orbital transitions. So IH1 to IE8, and so on and so forth. I computed position versus time graphs and energy versus. Sure.
Who is your audience? Whom you're going to explain it? Just tell. Sorry for a little sharp question from that seeming outside.
My audience is anyone who comes to my poster at the Sanibel Symposium.
How do they know what is IH1? How do they know what are these blue figures? You're jumping too much over the head. So you need to give some definitions before you get there.
Okay.
So, and I apologize for stopping you in the middle of your thought, but you'll be stopped anyway.
Okay.
The audience will be either stopping you or thinking that it is not interesting and leaving.
All right.
Which is not good. So keep going or adjust as
All right. So I'll go back to explaining a bit more of my background. All right. So I'm studying the thermoelectric effect. In order to do that, I'm computing the electronic relaxation rates for each of my orbital transition rates. So I guess what I should say is I should emphasize this hypothesis. That hypothesis is that the electronic relaxation rates will comply with the following band gap law. The electronic relaxation rate is e to the negative alpha delta e. Delta E is the energy difference between the initial and final states. So the reason I want to see whether these transitions confirm with the band gap law is that if they confirm with this band gap law, then it's relatively easy for experimentalists and scientists in general to compute the electronic relaxation rates. You know, it's much easier if they follow this certain law. We won't have to do like any experiments or anything like that. So that's why
I'm computing all these electronic relaxation rates to see if they comply with this band gap law. If they do, it makes computing them easier for scientists. So this work reports results on atomistic models. So these are lead telluride nanowires. They're doped with iodine and so sodium. I used density functional theory with the PBTE functional, and I used it. And I used Fast software to do my non-adiabatic calculations.
Question?
Yeah.
Are non-adiabatic calculations included in VASP? You do some homegrown codes.
I did my homegrown codes.
Okay, because from what you were telling, it sounds like non-adiabatic things are already included in VASP. You're using output of VASP to compute non-adiabatic processes.
Right. Let's see. Alright, so then these four orbital transitions were studied, and then I computed electronic relaxation rates for these orbital transitions to see if they confirmed with this band gap law. So I computed
orbital transitions. Why there are transitions between orbitals? Why electronic occupation experiences transition between orbitals? Which physical mechanism is behind it?
photoluminescence.
So you are explaining that transitions between orbitals convert energy from electronic degrees of freedom into photons, emit light. Are you sure it is what you are interested in, what you are describing? Ask David Krogman. He was answering this question an hour ago.
What's the question?
Communicate to each other.
What's responsible for electrons transitioning between orbitals? Yeah.
Mechanism. Why energy is being dissipated from electronic degrees of freedom? Where does go?
Is it going either photons situation and what we're looking at primarily photons?
Okay?
Alright.
So not photons, it goes into heat.
And that's phonons?
Yes.
Alright.
So right now, before you go to the last 5 lines of your abstract, please explain what is Vij in your methods. Thank you for putting this equation. It's the most important equation for all of us.
Vij, this is the non-adiabatic dynamics.
Or just coupling.
Right, non-adiabatic couplings.
Okay. So explain this equation and later tell what is a connection between phonons in this equation.
Okay, so this is basically the expectation value of the transition rates between an orbital with state I and an orbital with state J.
Okay. If the orbitals are orthogonal, should the occupation stay in orbital, let's say I, forever? Why it does go to orbital J? What's the mechanism? Why this matrix element is non-zero?
So going back to my understanding of quantum mechanics, if this state is the same as that state, then this should be not non-zero then.
There is a property of orthogonality. If you convolute orbital I and orbital j from orthogonal set, then it will be 1 if I equal j and 0 if I is not equal j. And here your I and j are not equal. But should it be 0 or non-zero? If it would be 0, then you wouldn't have your results. Right? There would be no transitions between orbitals. So why it is non-zero? And I apologize for a little discomfort, but it's better we run it now rather than in presence of judges.
Okay.
So DDT in the middle of your matrix, what does it mean?
I mean, rate of change in time.
Yes, so this time derivative is applied to what?
To this orbital right here.
Okay, why orbital should change in time? Why? Orbital should change in time.
Well, from my understanding, if you have an initial quantum system and you're putting energy into that system, whether it's by heat or you're shining light.
Quantum system put energy and then just you're too quick.
Alright. If I have an initial quantum system and I was putting energy into that quantum system by shining light or putting heat into it, then that electron absorbs that energy and then it jumps up into higher orbitals.
Okay, this is good. This is your preparation of initial state. But then you explore this electron in the orbital higher up, and you explore how does it jump back out of this excited orbital back to ground state orbital or through maybe sequence of other orbitals. So why these jumps are happening?
Because it's a tenet in quantum mechanics that when you excite an electron into a higher state, eventually, with time, it's going to go back into its ground state.
Philosophically correct, yes. But what is the mechanism? How does it go back to the ground state? And ask David. He was already given a little bit of hard time, and he tried his best to answer this question. He may help you, but ask him directly.
All right, David. How does it go back to the ground state?
Okay, we agreed on that. But Kevin is showing the matrix element of non-adiabatic coupling as time derivative of orbital. So why an orbital changes in time?
Because the nucleus moves.
If you don't comfortable, do not understand, ask him to repeat.
Can you repeat that?
Or
Because your nucleus is moving, or nuclei are moving as it relaxes, so the orbital changes at each step.
if you do not understand or you disagree, keep asking. It's the most important, the key part of what we are doing.
Okay, so you're saying that when an electron jumps into like higher orbitals, because these new nuclei move, you're saying their movement changes these orbitals?
Yeah.
How do these orbitals change?
They change because in different positions, the nucleus in different positions is going to result in different action. Or
So you're saying the nucleus moving results in that higher orbital having a different energy? Is that what you're saying, David?
keep talking, and I'll write a couple of questions and keep coming. But what you're talking is a really good thing.
So because the nuclei move, the resulting orbitals that you calculated, or however you decide to term, they're going to have to.
So initially, you're shining some energy into this electron. This electron moves into a higher orbital, but then these nuclei move, and that changes the energy of that higher orbital. So when the electron goes back down to its ground state, that ground state orbital is going to be different. If I'm understanding you correctly.
Then in the position they are when it's excited, yes.
So you're saying the final ground state is different than the initial ground state?
Yes.
Okay.
As you're exciting the entire system, not just the electrons.
Do you think it becomes more clear?
Yeah, kind of. I just have to go back through this talk a few times,
Okay.
and then it'll be clearer for me.
Okay. So you are not going to object Newton's equation, and you're not going to object Schrödinger equation, right?
Right.
So if your nucleus, which we will use with uppercase R, move according to Newton's equation, as we go along the trajectory, we go from position at time t to position at time t plus delta t.
Okay.
You agree, right?
Yeah.
Then at each position of nucleus, you run electronic structure code, and you are finding electronic orbitals that depend on the position of electrons and position of nucleus, because position of nucleus determine forces on electrons. So at time t, it will be one orbital and one energy. At time t plus delta t, the orbital will be different.
Okay.
And if you put these two orbitals together and put the DDT operator between them, t plus delta t, so t, it will be not equal to 0.
All right.
Okay? So as nucleus move, you solve Schrödinger equation or DFT equations for the orbitals, and orbitals will be different at each time step.
Okay.
So it shows interaction between electrons and nucleus. Make sense?
Mm-hmm.
And yes. And you are showing it here. It's just very shorthand notation, but this DDT means that your quantum orbital will be changed if you make an increment in time.
Okay.
Because it parametrically depends on positions of nucleus, and nucleus will be shifted even if you shift time.
All right.
Okay, let's keep going. Sorry for interrupting. So after you do have computed molecular dynamics with Newton's equation, and out of this molecular dynamics you have computed non-adiabatic couplings.
Right.
You plug them into Redfield equation and you find how the occupations of each orbital change in time.
Should I put the Redfield equation in my method section?
Oh, yeah, of course, yes,
Okay.
yes, it's your strength. You need to do it.
All right.
It's not like common thing, and you will be glorified by explaining it to the people.
Okay.
And then you do observables. So can you explain which observables
assuming you are showing based on the fact that you know how to find occupation of each orbital at each point of time. So you can find occupation of each orbital at each point of time. And out of this information, you find some observables.
Okay.
So please tell us about observables.
Alright. Before I do that, can I make a quick note about these orbitals?
Oh, please, please.
Yeah. Okay, so these are the orbitals I looked at. These are the electron hole orbitals. At the bottom is my electron orbitals. The bright green is my telluride. The dark green is my lead. And I'm doping them with iodine, which is right here, and then sodium, which is here. And all of these orbitals you see here are p orbitals, and they're all localized on telluride. All right. So I just wanted to make a quick note about that. And then here's my position versus time. I calculated these position expectation values for different orbital transitions and different temperatures. So I wanted to see how this expectation value changed with the temperature. So in this graph, I studied these graphs, and I noted that from these graphs, the temperature seemed to be directly proportional to the rate of migration. All right. So that's what I looked at. That's the main conclusion I got from these position versus time graphs and the position expectation value. And then I looked at the energy versus time graphs for my energy expectation values. And I'm honestly not sure what conclusions I could draw from that. So I'm not sure whether I should keep these graphs on my poster or not.
You definitely should.
Okay.
Those are your strengths. And we will go over analysis. Keep talking.
All right. And then I calculated the decay constants for my electron and my electron hole. And at the bottom on my graphs, go ahead.
Decay constants. How do you calculate them? Do not tell that you hit the button and the code spools the outcome. Which equation is used to get the relaxation constant based on these blue figures or green figures? How the rates of relaxation or decay constants are computed? What's the principle?
What equation I used to calculate my electronic relaxation rates?
Yes. You do have your hypothetical equation in your abstract.
Okay.
But it is not what is being done in your results and methods. You have some alternative way that eventually will bring you to this gap law. So, which equation is used to go from your green figures to your summary figures in the lower row? And David was answering an hour ago. You may try to ask him, formulate a question and check what he will try to answer.
All right. David, can you tell me what equation I used to get my decay constants?
Just teach him the basic principle.
So we're looking at the relationship of the electron position with this energy and time.
Okay.
Yeah.
So it's a question to both of you. And you're free to chat and ask help from group members. So in the green figures, you have green background, yellow stripe, dark blue stripe, and you also have the dashed line and solid black line. So what is the dashed line? What does it describe?
The dashed line, give me a second. The dashed line is my electron.
What do you mean about? There are different observables. There are different characteristics of it.
The energy of the electron.
Okay. Expectation value, average energy of electron at a given time.
Right.
Do you have an equation how to convert occupation of orbitals or distribution of electron as function of energy in time into expectation value of energy?
Is that the Fermi distribution?
No. If you have distribution and observable, how to find expectation value? Let's say distribution n of E and observable E. What will be the expectation value? Like if you have probability to find certain value of observable, how to find,
So it would be this, simply this times that.
you know? At which value of E? The E can take any value from minus negative to plus negative.
At which value would be the most probable energy?
Average value. Let's discuss it together, not in private. So, if you do have distribution, young,
Right.
it means probability that variable E has this value, this value, this value. How to find, if you take a measurement, what will be the most expected value of E? We multiply it by this variable and take into the so this value is not equal negative, this will be smaller, this will be increased, this will be, and then we need to find area under it.
Right.
And this will give you expectation value. Same as you find expectation values for the indicators all the time. You agree?
Yes.
Yes. So if you have distribution probability to find electron with given energy, the expectation value will be obtained by this.
All right.
Good. So your dashed line is this expectation value, which depends on time as well.
Okay.
So how to find the relaxation rate? How quickly this line is changing? If you have expectation value as function of time, and it does it changes from higher value to lower value, as you show in your lines. So dashed line always goes down.
Sorry, what's your question?
We agreed on the dashed line.
Right.
Dashed line changes in time.
Mm-hmm.
How to extract rate of electron relaxation out of this dashed line?
So would it be this final energy, which is here, minus the initial energy there, and then to divide that by time? That'll give you how.
Okay, well, it's excellent thinking. It's not quite precise, but in the very right direction. So you are trying to subtract change in energy, divide by change in time, and find a rate.
Right.
So basically find a derivative.
Mm-hmm.
Excellent. This is one of the ways. So one of the ways is to extract derivative and hope this derivative will be the same along the whole curve. Differential equation, differential way. There is also a way to assume that this curve obeys a certain analytical expression, like that it decays exponentially, and then fit this hypothetical formula into numerical data.
All right.
Let's discuss it a little bit more on the next iteration, but for now, your answer is cool, and it will just give a little bigger error bar.
Okay.
But if you take your dashed line,
Mm-hmm.
extract derivative of this dashed line, then you will get the points on your lower panels.
Okay.
Good. Now let's discuss your lower panels, what is shown and how you interpret them.
Okay, so for the decay constants for the electron, if we look at these 3 points here, which is 700, 900, and 1100. So for these three temperatures, the band gap law C seems to be observed. But then here, when we get into these lower temperatures, so for the 300 and the 500, we see here that the decay constant seems lower here. All right, and then for the electron hole here, from what I can tell, it seems like the band gap law isn't observed here. So I don't know if what I'm about to say is right, but it seems to me that at higher temperatures the band gap law is observed, but at lower temperatures it isn't observed. That's my conclusion from this data.
Cool, it's very interesting. Let's thank Kevin for presenting.
And other more questions or suggestions? I do have a suggestion.
Yeah.
So right now you have two panels for decay constants for electron, decay constant for hole. Would it be possible to make two panels more, like keep those and add two more panels by squeezing other information?
I guess I could squeeze like these graphs to make room for more.
Yep.
So you want those two panels to be methods and conclusion?
Maybe squeeze everything up, release a little bit space on the bottom, and make another two panels.
Okay.
Will be decay constants for electron and decay constants for hole. But right now, your x-axis is dissipated energy.
Right.
Can you represent the same data from the different aspect? Show temperature as x-axis.
So you want me to change this x-axis for energy to temperature?
Yes. Do not remove these figures. Keep them. Add two figures more. And right now you do have. So your data depends on it's function of two variables: temperature and dissipated energy.
Okay.
And function is your logarithm of rate. So you are showing the dissipated energy as x-axis and temperature as two different data sets. Right? Is it possible to swap them and make a new figure and make temperature as x-axis and different delta E as different data sets?
Okay. I think I can do that.
Yep. It may show interesting trends.
Okay.
Like it may show exponential decay with time explicitly.
All right.
Not with time, with temperature or growth. More questions? If not, I thank Kevin once again.
One comment.
Oh,
We get some data points are just not accurate. So if you look at the data corresponding to 500 and 700, the band gap of the 700 is even larger than 500.
All right. Yeah, I can double check that.
Can you mark it on the? So Kevin, please collect feedback from everyone.
Okay.
And try to implement what you see. We will have recordings of the meeting, and both there will be written comments from all group members, so
Okay.
that may help you to improve it further.
All right.
Okay. So, is there anyone who doesn't want to present poster next week? Okay, let's try to make updates during the week and present another version next time. Since it will be not the first presentation, but iterative, it will take shorter time, and we will then have two more interactions, next week and second next, and then your posters will be perfect.
Right.
They can be used for coming conference and for next conference as well. Anything else? Norsk is working, right? Having fun of it. Very good. So thanks much for investing your time, for helping each other, and looking forward to see you next week in this room, and maybe more often and frequent on a one-to-one basis. I'll stay here a very short time if there are some urgent questions, but otherwise we can set up time for during the week.